In this video, we'll move on and consider a second property that we'd like from our projects before they can be put into production. Namely, that we can explain how they work and explain the predictions or decisions that they lead us to make. There are many reasons why you might need to explain the behaviour of a model before it can be put into production. As an example of this, we can consider a credit scoring system that determines whether or not some customers should be given a line of credit. So what exactly do we mean by an explanation in this case? Well, it's likely not going to be the same thing depending on who it is that we're talking to or about. As a data scientist, we might be interested to know exactly what types of mapping between covariates and responses can be represented by the neural network that underlies this credit scoring system. Stakeholders might need an explanation that lets them know the general behaviour of the model across large numbers of loan applicants, and they're likely going to be indifferent to the technical underpinnings. Finally, an individual customer might have some investment in the overall behaviour of the scoring model, but they'd also probably like to know what actions they can take to increase their chances of securing a loan. Or if they've been denied a loan, they'd like to know why that is. Between each of these examples, the level of technical detail differs, but more importantly than that, the fundamental nature of the explanations are different. So with some models, giving an explanation is relatively straightforward. Decision trees are perhaps the easiest model to explain because they mimic human decision making and can be represented like flowcharts that give a sequential linear partition to the predictor space. These models use the same sort of logic that is present in a medical triage when you call an ambulance, for instance. A series of binary decisions is used to determine the urgency of the call, and the questions that are asked and the order that they're posed in are optimized to identify critical calls as soon as possible. But this is just one form of loss function that we could use to optimize this system. Instead, and more generally, we might pick these partitionings to get the most accurate overall classification of calls into the correct urgency categories. This mightn't be appropriate as a loss function for ambulance calls because we're getting the most benefit from triaging the most urgent calls first, but when deciding which loan applications to grant credit to, it might be a more appropriate metric. The issue with these sorts of decision trees is that they're very limited in the sorts of relationships they can represent. They can only make linear partitions that are perpendicular to one of the covariate axes. This means that things like linear relationships have to be approximated by a step function. These methods are also very sensitive to small changes in the training data, and to overcome these deficiencies, we can use techniques like bootstrap aggregation or a random forest model to make predictions based on a collection of these trees. This is going to lead to models that are more stable and flexible, but also removes any chance of a simple and human-friendly explanation that's present in a simple decision tree. Another model that's relatively straightforward to interpret is a linear regression. We can interpret this model using the estimated regression coefficients, which describe how the predicted outcome changes with a unit change in each covariate, while the values of all the other covariates are held constant. In this way, it's global and a conditional explanation. It's a global explanation because the effect of increasing a covariate by one unit is the same no matter where the starting value of that covariate was. The explanation is the same in all parts of the covariate space. The explanation is conditional because it assumes that all other covariate values are being held constant. We'll see shortly that this can lead to some odd behaviour in our explanations because it means that they're dependent on what other terms are included or left out of our model. A contrasting model here would be a nonlinear regression, where covariate effects are still interpreted conditional on the value of other covariates, but the size and direction of that effect might vary depending on the value of the covariate. We've got a conditional explanation, but it's now a local explanation. We can see an example of this in the figure, where a unit increase in the covariate is associated with a large change in the model response for low values of the covariate. But if we're starting at a higher value of the covariate, then that's going to result in a much smaller change in the value of the response, for the same change in the predictor. So from these two examples, we can see that both height and volume of a tree are positively associated with the girth of the tree. And this makes sense, right? Taller trees are generally wider around the middle, and trees that have a greater total volume are probably going to be greater in circumference. What's interesting then is when we include both terms in our model, the interpretation of our coefficients changes dramatically. Here, height is no longer positively associated with girth, and in fact, the sign of the point estimate has changed from positive to negative. This is because for a fixed volume of wood, a taller tree is generally going to have a smaller diameter. When we think of it this way, it's not so surprising, but it's quite easy to forget that the size, direction, and significance of our estimated effects in a regression model is conditional on what other terms we choose to include within that model. There are some interesting techniques, such as SHAP, which try to quantify the importance of a predictor by averaging over all possible combinations of predictor that might be included within the model. If you'd like to learn more about techniques like SHAP, you can check out the section in Interpretable Machine Learning by Christoph Molnar. So this effect of changing signs is related to something known as Simpson's paradox, which you might have come across before. This is where a trend appears in several groups within a dataset, but that trend either disappears or reverses when those groups are combined. Something like this regularly arises in fields such as epidemiology, where population-level trends are assumed to apply at the level of individuals or small groups. And in this case, this same effect is known as the ecological fallacy. Actually, it's quite important to note that Simpson's paradox is a terrible name because it isn't actually a paradox at all. It's not super surprising that we have two different answers to two different questions. This supposed contradiction is only arising here because we fail to distinguish between these two subtly different questions. What I hope I've managed to highlight here is that for even some of the simplest models we might want to use as data scientists, explanations are very much possible, but we must make them with care and pay a great deal of attention to detail to correctly interpret those models, and this can be far from straightforward. So at this stage, you might be asking yourself, what hope do we have of explaining more complex models like random forests and neural networks, given how much difficulty there has been to explain even the simplest models that we might use as our benchmarks? Well, I'd say you'd be right to be worried about this, and it's important to remain humble in what we can and we can't know about these complex systems that we're building. All hope isn't lost though, we still do have a few tricks up our sleeve that I'll get onto now. So suppose we've been asked by our product manager to determine which predictors or covariates are usually the most important in our model when determining whether to give someone a loan or not. One way to do this would be to remove each covariate from the model and investigate how that changes the predictions that are made by our model. However, if we think back to that tree example, we've already seen that removing a predictor can substantively change the interpretation of some models. So instead, we could answer this question by using something known as a permutation method. If we take all the observed values of a covariate, say the income of our loan applicants, or the volume of this set of trees, we can then randomly allocate those between all of our instances, and this will destroy any association between income and loan outcome, or between volume and girth. We can then assess the importance of our predictor by fitting our models again with this modified training data and investigate how much our performance metrics are degraded by destroying this relationship. What this allows us to do is remove the information provided by this predictor without altering the overall structure of our model. There's loads of situations where this sort of permutation test can be really quite useful, and they provide really powerful and simple tools for understanding the behavior of our models. An alternative strategy to understand complex models is to construct something known as a meta-model. As the name suggests, these are models of models, and they can be effective methods of providing localized explanations for these sorts of complex systems. So the main idea here is to look at a small region in the covariate space. Since we can't easily give a global explanation for a complex model, we're going to focus in on what is happening in that region, and we're going to interrogate the model's behavior within that range. Based on a set of sampled inputs and outputs, we're going to construct a simplified version of the model, a meta model, within that interval that lets us explain what the model's doing in that localized region. Often this meta model is chosen to be a linear model. This is partly for convenience and familiarity, but it's also got a really sound theoretical backing. If our complex model that we're trying to make a model for is sufficiently smooth, then that means we can appeal to Taylor's theorem to say that in a small enough region, that complex mapping can be well approximated by a linear function. This is a trick that physicists and engineers absolutely love. So if you're working with a team involving those sorts of scientists, then this will go down an absolute treat. This sort of local model explanation is going to be particularly useful if we want to explain individual predictions or decisions that our model makes. So, for example, why a single loan applicant wasn't granted their loan. By constructing this sort of localized linear model and then inspecting the coefficients of that surrogate, we can identify which of the covariates are the most influential in that part of the covariate space, and use that to suggest how the applicant could increase their chance of success. Of course, we've got to be careful here and only report the covariates that the applicant actually has some ability to change. This sort of local approximation is exactly what's taken by the LIME methodology that was developed by Ribeiro et al., where LIME stands for Locally Interpretable Model Explanations. So using our local or conditional explanations for our model's behavior can be useful in some circumstances. What they don't give us is a broader understanding of what's going on overall. We miss out on the big picture. What if we actually want to know how a covariate influences all outcomes, not a particular one? Or what if we care about the covariate's expected effect over all loan applicants, or the distribution of effects over all applicants? While it might seem like these local and conditional explanations are lacking here, it's actually a place where they can behave particularly nicely with a bit of computational effort. By making these local conditional explanations at lots of points in our covariate space, we can then aggregate those explanations to understand the global and marginal behavior of our models. To do this aggregation, we're going to have to integrate these local conditional effects over the joint distribution of all the covariates. If this sounds a bit scary to you, then you're right. Integration is hard enough at the best of times, without adding in the fact that we don't even know what this joint distribution function f is. But in a way, this is actually a benefit for us. We don't have to worry because we can take the easy way out and do both of these things approximately. We can approximate the joint distribution of the covariates by the empirical distribution function of the covariates that we observe in our sample. And then this has the really nice property that it simplifies our nasty integrals down into just the average over the measurement units in our data. So in this case, our loan applicants. A particularly nice feature about doing this over all of our measurement units here is that it's going to appropriately weight each of our local models within the sample according to their frequency within the sample, so that explanations that are more common get greater weight in the overall explanation. This is, of course, assuming that our sample is representative of the population that we care about. So let's recap what we've covered and wrap this video up here. We've seen that our models, as they become more flexible, also become more difficult to explain, whether that's to ourselves, to a subject matter expert who wants to check that our model's doing something sensible, or to the end user of our model, who might want to know how it's being used to influence decisions about them. This isn't to say that simple models are always going to be easy to explain or interpret. Simple models can be deceptively tricky to communicate accurately. The last thing we looked at were a couple of techniques for explaining more complex models. We can use permutation tests to measure feature importance within our models by shuffling the predictor values to break up any relationship to our response, and then measuring how much this degrades our model performance. A big reduction here is going to imply that our feature was doing a lot of explanation. We can also look at the local behavior of models by making surrogate or meta models that are interpretable and aggregate those local models to understand the model behavior globally. Being able to make effective explanations is an essential skill if you want your models to be used in practice and feed into real decision making. While this does require some skill with rhetoric in order to appropriately tailor your explanation to the person that requested it, this is not a soft skill. It also requires a surprising amount of computational and mathematical ability to extract these explanations from complex modern models. Thank you very much for your time, and I'll see you in the next video.